Hi! And welcome to According to Pete. I gotta remember what the show's called. Today we're gonna talk about some PCB layout practices and just give you some guidelines and things. But before I do, there's a couple of things I want to mention. The engineering department has its own Twitter account now, SFE_engineering. So definitely check that out. We will be general spouting of nonsense, things that we're working on, upcoming products, probably some giveaways. In fact, I was just at a conference called Small Satellite in Logan, Utah, where I gave away 100 Arduinos, and I tweeted out, albeit on my own personal account, that we're giving away Arduinos, and a lot of people showed up, so it was really cool. Second thing I want to tell you about is this. Wow! We have our very own SparkFun engineering mug. It is for coffee. You can see it's got a funky graphic on that, made by our own Pamela Cortez. Thank you, Pamela. And the only way you can get this is by helping us with product revisions and making things better, right? So if you're on GitHub and you're checking out our code and you're improving it for us and you get some of your code pulled back into ours, or you're doing layout work and we incorporate some of your changes, you're going to get one of these, okay? That's the only way to get it. Now, let's talk about PCB layout. The original question that got me running in this direction was somebody asking, hey, can you do like a comparison of all the different PCB layout programs? Well, no, I don't know them. In order to do that effectively, I'd have to know several fluently, and I don't. I don't. So I'm going to assume that any program that you use, you've got at least a little bit of experience. You got how to lay out a trace, you know how to do a schematic, We're going to talk about the PCB and how you sort of piece it together and some rules of thumb that I go by. The first thing to talk about, mechanical prerequisites. So for example, is there a shape that the board has to be in, right? I mean, if you got it fitting into a specific enclosure, that shape is going to be a constraining factor. The mechanical components, like a potentiometer or a switch or a jack of some kind, right? Where do those have to be? So for example, and I'm just going to assume that I'm putting it into a square box. Hey, it looks like this. That's not a square, Pete. So for example, you start to think about like, okay, well, how am I going to use this? You got to start thinking about that. How's the signal going to flow? Where are my inputs? Where are my outputs? How's the power going to get in? So you might do something like, you got a jack here of some kind. Maybe this is a barrel jack. You might put a USB here. You might put a slide switch here. And then maybe you've got some ports up here. And like I say, this is going to depend on what you want to do with your circuit, right? So you might bring inputs over here, and you might put outputs over here. You might have an RF jack, for example, like an RPSMA for 2.4 gigahertz. So that's going to have to hang off the side, sort of like yay. So, okay, these are going to be the beginning constraints of what you're going to build. And now once you have this idea down, you've got constraints for the space where your circuit's going to go. And you've got a fairly decent idea of where your circuit sections have to go. Copper weight, right? When you get a PCB made, you can get what they call 1 ounce copper or 2 ounce copper on it, and maybe there's more, but I haven't seen them. And what that means, and I didn't know this until yesterday, is that if you were to take an ounce of copper and pound the bejesus out of it until it's absolutely flat and covering 1 square foot, that's the thickness that this would be. What that comes out to be is about 1.37 mils, which is thousandths of an inch, so it's real small. 2 ounce copper would be twice that, okay? At SparkFun, we use 1 ounce copper pretty much universally because it's cheaper and we can get the job done pretty well that way. Then, of course, we should talk about how many layers your board has. Now, we do have a few 4-layer boards, but 4-layer boards tend to be more expensive. So we generally do everything with a 2-layer board because it's inexpensive. And most of the circuits we do are easy enough to do as a 2-layer board, but we do use 4 layers in some cases. What a 4-layer will get you is potentially a dedicated VCC plane in the middle and a dedicated ground plane in the middle. And that's a cool thing because you never have to worry about stringing weird traces places to get things done like you do with a 2-layer board. You also get the additional capacitance between the 2 layers, so it'll act as a little bit of a filter, right? So you're decoupling everywhere. Trace width. A lot of times for low current traces, and a trace is just, a thing that completes a circuit. I don't know why you would go to that. Doesn't matter. Anyway, how thick is that? Generally, if it's a low current path, which is to say we don't expect it to be running any more than about 20 milliamps, we try to stick with 10 mil traces, 10,000ths of an inch, okay? If it's over 20 mils, you got to start increasing it a little bit. Circuitcalculator.com. You can put in like a current that you're going to run and how heavy your copper is, and it'll tell you how big your trace has to be. And generally, a 10 mil trace is good to about 30 milliamps before it starts to become resistive and a problem. Other thing, don't use an auto router. I mean, if you can help it, right? Because auto routers do things like, hey, you want to trace over there? Okay, there you go. Okay, that looks awful. And that's an antenna. Okay, so you don't want that. You want to keep your traces nice and elegant, and an auto router is generally not going to do that for you, so you probably want to stay clear of that. Another thing that we do is we tend to avoid right angles in our traces, and the reason is because a right angle in a trace, what it will actually do is round your edges. Like that. No. So if you're running logic, which everybody is these days, right? A trace with like a lot of right angles in it is gonna ultimately round an edge, and of course logical devices read edges, so you need that edge to be relatively intact. And understand that this is a probabilistic sort of thing, right? I can't tell you that if you run a trace from here to here and you put a right angle, oh my gosh, that's not going to work. All right, it's just going to round it a little bit. It'll probably be just fine, but it's the sort of thing, it's a rule of thumb, right? You watch these sort of things and you try to avoid that because you don't want to run into issues. You want to keep the probability of issues down, so you don't do that. Parts, individual, you got a schematic, you got a pile of parts to put in your board, right? The sections of the circuits are, they're going to be arranged on the board, like you've got a power section, you've got an amplifier section, you've got a microcontroller section, you've got sensors or RF, right? And these sections are going to be placed on the board according to their position in the signal chain, okay? And they all got signal chains of some kind, right? So, for example, I started out here with some headers here and some headers here, and I said rather blithely, this is going to be your inputs and this is going to be your outputs. Well, something like that. Honestly, I'm sitting here looking at this going, I would not do it this way. I would rearrange it. But you might have, a system with an accelerometer and a microcontroller and a USB, right? Okay, so there's your signal chain from input, which is the mechanical, to the output, which is the USB. Or it might be, a sensor to a micro to a Bluetooth or a Wi-Fi or an XB, something like that. There's your signal chain from, front to back. And that's going to dictate, where these sections go, because you want the circuit to flow well. And quite honestly, you build the circuit stages according to the schematic. I mean, you literally look at, okay, I've got, an op amp in the schematic here, and I'm going to put these components here because they're close by, and that's critical. And that's how you sort of put stuff together, right? And it sounds obvious. I know it sounds obvious, but you'd be amazed at how many times I see somebody who hasn't done a lot of layout before, and they'll put like a microcontroller over here, because I wanted to save space. And then they'll put the crystal. What are you phoning home with that? I mean, look at this. No, you don't do that. And the reason you don't do that is because this thing is an oscillator, and that's an antenna. And it's going to scream out to everybody across the galaxy that you don't know how to lay out a board. And in fact, while I'm on the subject of microcontrollers, another mistake that I have seen many, many times, thankfully not by our guys anymore, is that on any schematic you will see a microcontroller, right, as some piece, and then you will see like a bank of caps, and this is the schematic, right? And they'll all be like, 0.1 microfarad, and there'll be all of them, and they're all tied to VCC, and they're all tied to ground, right? Okay. Now, a lot of times in the schematic, you'll see it says near pin such and such, referring to the microcontroller. And what some people will do is they will just say, well, I could just put all those together in a section, right? So you got your microcontroller over here. Oh, well, I had some room over here, so, you know, I put all my caps here. No, you don't do that, all right? A microcontroller, if you look at the pins, every time you see a power pin on this thing, there's going to be a ground pin really, really close to that power pin. And the reason is because they want you to put a cap right there, right? That is to minimize the length of those traces and to decouple noise on the power supply to ground. So it's important to keep components that are related to a certain circuit section close to each other. You want to keep those traces short and elegant and nice. The first section that I generally start with is the power supply, which is to say a regulator, a switch, maybe a fuse, decoupling caps, so like a 0.1 ceramic and probably a 10 or 100 tantalum, something like that. Those are just general parts that you might find in a regulator circuit. When I started this out, I identified this one as USB. I identified this one as like a barrel jack. So this is where the power is coming in. And I've positioned these, this is a switch, if we can call it, I don't know, sure, it's a switch with a thing hanging off. So the barrel jack will be near to the switch, and you'll run power, you know, to the switch, and then, you know, like that. The switch is almost certainly going to be close to the power jack, unless you're doing something that's like touch sensitive or you've got like a soft stop on it. This is a hard stop. I want to cut off all the power from this circuit board. Your circuit may vary, but this is how we're going to do the example. So now what? Well, generally, just like the schematic's going to show, probably, is it's going to have, you know, a cap on the input, then probably, you know, a TO220 or a SOT235 package regulator, like a small current regulator, and then a cap on the output, maybe another cap on the output, ceramic and tantalum. And so what I will normally do is I will pack that circuit section off, right? So I'm probably going to run this too, you know, and there'll be one cap, and then the regulator might be here, or actually, right, this is an iterative process, and I'm iterating right now. So I might put like the SOT235 there, and then this will run over here to the input. There'll be pin 1, 2, 3 on that. The output's going to be over here, so I'm probably going to have, you know, another cap down there to ground. And then I'm out, okay? Now the point of this is to find like a good place out of the way that the power supply can be, and then feed all the other sections, okay? And like I say, you want to do this according to what the schematic shows. You want components that are close electrically in the schematic to be close physically on the board. How do you feed these things? Generally, when I do it, I will do sort of a modified star configuration. And a star configuration is just that each section gets its own dedicated line back to the regulator, right? Now, in the schematic, there's going to be a zillion different places potentially that VCC is going to need to go to. But you cannot realistically run a line from here to every last component that's got to be covered by VCC. Now, if you're running a 4-layer board, much easier because you got a layer of copper underneath that you can just punch down to. That's my VCC. It's easy. I can get it anywhere. 2-layer board, you have to plan a little bit. Now, your sections, right, you're going to have like a microcontroller section. You're going to have, let's say we've got sensors, right? If I had an RF link, I would probably keep an RF module over here. I might put my microcontroller sort of here and maybe orient it so the crystal was nearby there, a couple of caps that decouple. And then I might put like sensors here, maybe a multiplexer. I'm making this up as I go, right? But your sections, right, this is going to be your RF section. This is going to be your microcontroller section. This is going to be the sensor section. And the way you want to feed these things is by section on the schematic, right? So for example, if I had an op amp, and I've got an op amp for example here, there's a few different places I want. Let's say I've got an op-amp section, here, and I got a couple other components, and those things are strung out. What I'm going to do is I'm going to run like a single trunk line to this point, and then it's going to diverge to the different parts in the circuit where VCC has to be, right? The reason for doing this, obviously, I don't want to run three lines back here. But if I can tie all three of these points to a common point, then each of them equally gets a feed from VCC. Now, to back up and remind you, why do we do this? Because if you're daisy chaining components, like I've got VCC here, and it's going down to something here, and then it's going down to something here, and it's going down to something here. Well, if this guy draws a lot of current, these two guys are going to feel a voltage drop. Okay, not a huge one, but it's going to introduce noise. So every time whatever this component is draws a bunch of current, these guys are going to feel it. So what you do is you tie them back up to here, or at least so that they are, equidistant in a way. And by doing this, you tie them all to a center point there. There's your star, and it's fed by a single one. Now, earlier I said 10 mil traces. We try to keep to 10 mil traces, but this big trunk might be feeding more than 20 milliamps, so I have to keep that in mind. If it is, I might up it to 12 mil, 15 mil, 20 mil, depends. So I'm going to keep an eye on that. And each section will go back this way, okay? And so there'll be one to the micro section as well. And a lot of times I'll run this directly under here and then feed the different power pins. So it's all very equal, okay? You want to build the circuit stages, the circuit sections. Really, you just want to follow the schematic, right? So, and like I said, the parts that are close to each other electrically, you want them to be close to each other physically on the board, okay? So as an example, I drew up a quick op-amp circuit. With this, I drew a SOIC 8 service mount op-amp part, LM358, 2 op-amps on it. I'm using 1. Here's our schematic. We have R1, R2, which set the reference, R3 and R4, which set the gain. We have C1, which filters our reference, and we have C2, which decouples the power supply on the op-amp, okay? Now, how many places do we have to feed stuff to? We have 2 places where VCC has to go. It has to go to the top of the voltage divider that sets the reference, and it has to go to power the chip, okay? So I got 2 places VCC's got to go. How many places do I have ground to go? I got 1, I got 2, I got 3, I got 4 places, okay? So when I put this circuit together, I'm going to try to minimize the common points so that I only have 1 feed point instead of 4 feed points. I got 1 place where signal has to go in and 1 place where signal has to go out, okay? So I can picture that in my head geographically. I'm going to want signal going in on one side of it physically and signal coming out on the other side physically, because it's going to have to go to the next stage, right? I don't want it circling back around and have the input and output next to each other. I'll start with the critical ones. Anything that attaches to one of the high impedance lines here. Those paths have to be pretty tight. You try for tightness. You try to keep them very close, right? Start with my feedback, right? Pin 1 is the output for one of the 2 op-amps on that chip. And I've got R4 that goes straight over to R2. So what I've done over here is I've placed this guy, and this represents R4. R4. So I would put this guy right on those 2 pins. The next, it's like, and I've got my signal in also going off of R2. So I placed R2, it's sideways, what are you gonna do? Right there. So I can get to pin 2 electrically, right? And I will just run like a small trace to these points. Aha, pin 3. What have I got on pin 3? Well, I've got 2 components. I've got R2, which sets the reference voltage with R1, and I've got C1 that filters. These both go to ground, so I can put those 2 components right across pins 3 and 4. So right there and right there. Now, on the SOIC package, you've got VCC on one corner and ground on the other corner. So it's a little difficult. If you're putting components on the opposite side of the board, this is an easier thing to do. Most of our boards are single-sided that way. So it's a little trickier. So what we've done in the past is we'll put the cap, the filter cap up here and run that to there. And then, you know, if all the traces for this op amp are coming off over here, you can run a trace down over to here. And that's about as minimized as you're going to get. Now there's this guy, R1, that goes from VCC to pin 3. Now, as you see, I've got VCC all the way over here. So I've got 2 points where I have to get VCC to, but I can try to minimize it, all right? Now, I know that it's got to go to the top of R2. I've done something wrong. Wait a minute. Sorry, there's my mistake. That's R3, not R2. This is R2. This is going to be C1. Where would I put R1? Well, the best place electrically would be to put it probably close by in here so that you minimize that current path. And I probably wouldn't run it there. I'd probably run it to there. Then, of course, I've got to get VCC there and there. So I need 2 feed points. So what I would probably do on a PCB is I would string my trunk, arbitrary trunk, off to a single place and then run a trace up to here and a trace over to here, okay? So that these lengths are equal, and then, you know, that way neither one of these things, if it starts to draw current, will cause noise for the other. This being an op amp, a 2 op amp package, you don't want to leave these pins float, okay? This thing will oscillate like a thing that oscillates a lot. So what you're going to want to do is tie those lines. You know, there's let's see, 5, 6, 7. I think the out is here. I can't remember it. I have to look at the data sheet to remember it. But the inputs of this thing, you're going to want to tie either to ground or to VCC or one to the other. If you put in unused op amp into Google, you will come up with a zillion different pictures of how people manage to lock these things down so they don't oscillate. This is just one example, but every circuit section is basically the same by rule. You want to keep the components that are close electrically, close physically. So, for example, like I was showing you on the microcontroller, you want to keep those decoupling caps very close to the pins that they have to act upon. In the case of sensors, same thing, you know. Decoupling caps are the biggest ones I'm probably going to talk about. But any resistors that have to do with the particular components, you want to keep those local. You want to keep, you know, any traces that are not the input and output to the section, you want to keep all that stuff close. So you got your board, and you got, in my case, I had my power supply down here, and then you will just run your sections, you know, according to how you've got your signal chain hooked up. And then, you know, you're running into here and out and in and out and in, and then, you know, a port here. And that's kind of how you do it. So let's talk about ground and how we get current back. So the whole bottom of the board will be copper or thereabouts. Typically what I would do is I would lay down all of my signal traces first. And some of them inevitably will go on the bottom from component to component. You know, that's just the way it happens. You're going to have, like, you try to keep it all on top so you can keep the bottom all copper. It's never going to go that way. You're always going to have a few traces on the bottom. And then the easiest thing to do, which is not necessarily the correct thing to do, but it's the easiest thing to do, is to lay a huge layer of copper all on the bottom. And every place that you have in your circuit that has to go to ground, you just punch through with a via and you're at ground. You should be running your DRC all through this. DRC is design rule check, okay? It's gonna tell you if you've got any dimensional problems. It's gonna tell you if you've got any air wires. It's not going to tell you something about, hey dude, your return path is stupid and you should fix it. What do I mean by that? The return path is where your current is coming back to the power supply, back to the regulator, for example, which in our example is down here, okay? So on all of my circuit stages, I'm going to be looking at how much current the stage is drawing and what the current path looks like. If it's a low current return, I'm probably not going to worry too much about it because there'll be enough copper here that it'll find multiple paths. And of course, it'll use, you know, the path of least resistance. Plan on that. But if I've got a whole slew of other traces here, you know, and I'm powering something out here, what's this return path going to look like? Well, it's going to follow the copper kind of, and you want to watch for stuff like that. For low current stuff, it's not too bad. You can make that compromise. But, you know, if I'm drawing, you know, 30, 40, 50 milliamps to something out there, I don't want a return path that looks like that. I want it to be a little beefier, and I want it to be straighter. Some of you might be going, what? No VCC plane? Well, no, right? Remember, two-layer board, but you can have VCC on the, was that 3 Cs? VCC, on the top of your board just fine. Well, you can, but it ends up, I mean, you're going to have a lot of traces on the top. We have a lot of traces. When I lay out a circuit board, I have a lot of traces on the top. And it's harder to maintain a full plane of VCC that way. Not only that, once upon a time I got bit by a situation where we had a VCC plane on the top, and the solder mask came back a little wonky from the fab house, and there were shorts to VCC everywhere in the circuit, and we couldn't trace it. So ever since then, I'm real shy about putting a top layer VCC plane. Again, don't assume that after you run your DRC, if you've got no air wires, that does not mean everything's cool. Watch your ground returns, okay? Now, after that, we talk about aesthetic things like silk, right? Between the time that you submit this board for prototype and the time that you get it back, you're going to forget everything about this board. So put some silk on it, right? Make it meaningful. So if you've got headers up here, label your pins, right? I mean, ground VCC, or I mean, not ground VCC, but like USB, you're going to know, obviously. Power in, you're going to know. But any place where you've got like a bunch of different signals, label it, because you're going to need it. A lot of times, the CAD program like Eagle will, by default, put component labels. Like if I got a resistor here, it's going to say that's R3, and it's going to put it in the silk automatically. At SparkFun, we don't really do that because we want the boards to look really nice, but if this is a board that I am actively working on and I need to get in there with probes or an iron to rework or what have you, I'm going to want those. So think about that. Think about what your silk is going to be. Think about how it's going to help. So you run a prototype, you get it back and you build it, and then you test it. When you test, limit the current on your power supply down to 100 milliamps. Like when you build it, you're going to have a rough idea of how much current it's going to draw right off the bat. If you've got no input and no output, it's like 30, 40 milliamps when it's running quiescently and I've got nothing going in or coming out of it. So what I would do is I would probably set the limit on my power supply to 100 milliamps, 75 milliamps, something a little bit above, but not so much that anything's going to burn, right? And then I know that when I hook up power, if the power supply goes into a rail situation or a limiting situation, I know I've got a short and nothing has been destroyed, okay? Now, another way to do this is with a meter. You just take a meter and put it from ground to VCC and you check to make sure it doesn't say 0 ohms or various other places in the circuit. If it doesn't do what you want it to do, you got to go back and find out why. And you might have to redesign, relay out, get in there, give them hell. So there it is. Hopefully I didn't add confusion to an already confusing topic like I sometimes feel like I do. Don't forget to check out SFE Engineering on Twitter. Go check out some of our code and our layouts and see if you can help us out, and maybe you can get your own coffee mug. Comments, go in the comment section below. You can load it up with whatever you like. Questions can go there, comments can go there, or you can send them all to feedback@sparkfun.com with "according to Pete" in the subject line. So, until next month, take it easy. I've consumed almost 34 ounces of coffee this morning. I love this mug.